really. One is using this method called recurrence analysis that I described. It's a very simple technique, the way that we use it at least, to look at coupled attention between persons, to do just what I described. We're going to look at the dynamics of visual attention between two people and how that coupled attention reflects higher level linguistic interaction. And then following that, I'm going to talk about a study with Max Laursa on the multimodal dynamics that hold in discourse. So as my conversation topic changes, as I decide to give you directions versus explain some complex concept to you, what will happen as I change the topic of conversation is you'll get corresponding change in the multimodal dynamics that take place. Specific gestures will tend to occur in specific ways, while certain kinds of facial expressions may change and so on, because these systems are interdependent and flowing together dynamically in time. So before I jump into those empirical studies, I'm going to explain recurrence analysis to you quickly. This is a summer school. Many of you know this technique. Some of you may have even seen these slides, but I want to make sure that everyone's on the same page with this kind of lag-based technique, which we use because of its essential absence of any statistical assumptions and the fact that you can deploy it easily in the multinomial context, as you'll see. Now, alignment in psycholinguistics has been an extensively discussed characteristic of interaction. And you can see this in this little picture that I ripped off Flickr a while ago. These two people might be at an art gallery, hanging out, and they're already exhibiting what some folks in the psycholinguistic sphere refer to as a kind of alignment. So their postural position is shifting or converging in some similar way. They're leaning into each other. They're holding their glasses in the same hand. They're contorting their face in similar strange ways, as humans do. They've locked glances. This is relatively sort of perceptual motor alignment, but there's been an exploration of higher level kinds of alignment as well. So if you imagine these two folks are at an art gallery, she might say, "I just love Slim's artwork." And he might respond, "Oh yeah, just love him, profound." Right? And so this is what Greg Bryant would refer to as an ironic exchange, I believe, is that right? yeah, exactly. So this happens, I'm not just making it up. But the idea, of course, is that all of these are levels of, essentially they're levels of measure that many of our studies in linguistics entirely justifiably isolate and analyze into themselves, but they're all sort of cascading and changing together simultaneously. So I'm just going to show you quickly modeling this kind of thing just to explain the method of recurrence analysis. And so let's just imagine we're going to focus on one of those channels, and these channels can take one of three states, A, B, or C. So this might be, for example, topic of conversation. So we meet at a bus stop, and we need to activate a node that lets me know what I can talk to you about. What can I talk to you about at the bus stop if I've never met you before?
The weather.
Yeah, wherever you're going, everyone talks about the weather. All right, so that's the idea, of course. Now we activate that node and we begin to talk. But the idea, of course, is that this is just a very simple attractor network, call it a symbolic oscillator, but we can couple them according to some strength. And so the idea is that we can simulate turn-taking, and they're under intrinsic noise, so they'll bounce about. But after, in some conditions of the simulation, we might increase the strength in such a way that they effectively constrain each other's behaviors. It's a very simple sort of simulation, but it's modeling this idea that we're coupled to each other. And the decision I make is going to suddenly influence the decision you make in such a way that you might align with that decision, which will influence me, and then we'll bounce back and forth, generating a similar pattern of behavior. So we can simulate this kind of system very easily to demonstrate this recurrence analysis method that has a wide variety of applications, only one of which I'm going to describe in the talk today, but I'd be happy to speak with everyone about because I have a variety of slides and so on for other kinds of applications of this. And recurrence analysis has two steps. Step one is plot and visualize the co-occurrence of patterns in a recurrence plot, and the second is to quantify the way those points on the plot are occurring. So let's just demonstrate this to you in straightforward ways. So I'm going to simulate that little artificial system. And let's just start where there's no coupling strength between those two systems at all, and they're only under intrinsic noise. And up here on the top right, you're going to see a sequence of red states and a sequence of black states. They're just meant to reflect these two networks I just showed you, woman and man. And when they're under intrinsic noise, these systems just bounce about wildly without any seeming structure. And so a recurrence plot, step one of recurrence analysis, is to plot points of recurrence between these two systems in time. So just to describe it simply, we take this the red time series and just plot that along the x-axis, and the other time series or symbolic series, category series, normal series, take your pick, along the y-axis, and we simply draw points on this plot when they match in time. So at this relative time, they are both in state C. At this relative time, they are both in state A. But she was in state A just a little bit later on as well. And so we do all of these comparisons in time, and we construct what's referred to as a recurrence plot. This is a cross-recurrence plot. These are two systems, and we're conducting this sort of comparison, but I'm just going to refer to it as a recurrence plot here. So this is a visual portrait of the temporal structuring and their behavior. So if we increase the strength of this network and just watch the behavior unfold, you'll see changes in this plot that are pretty much predictable from this very simple extension of, one could call this discrete recurrence. You can see structuring taking place along that main diagonal. And the networks are beginning, because the strength of coupling between them is they're beginning to influence each other, they're essentially falling into these topical attractors and they're trapping each other. But then occasionally noise pops them out and they follow each other around. And so these are the plots coming to look symmetrical. Because if two systems are synchronized, or they're aligned in some way, we would expect points to fall along this line of synchronization, because this is comparison at the same time. Sometimes referred to as the line of synchronization or line of coincidence. So if these two systems are coming to exhibit the same behavior at the same time, we should see relatively symmetrical structure and a high density of points along that line of synchronization. And so as the connection strength increases, you can see this wonderfully. These blocks are reflecting kinds of topical attractors between these systems. And so there are quite a lot of things you can do with this kind of recurrence plot. This is an extremely simple, extremely simple demonstration of just constructing the recurrence plot. But this method, recurrence analysis, is based fundamentally on quantification of the points on the plot. So we don't simply eyeball what this looks like. We say, oh, here's the coupling strength. That looks interesting. It looks as if there's some structure along that main diagonal. They seem coupled. What we do is we quantify the distribution and concentration of points on this plot. And so there are all kinds of things you can do here, but we do a very simple thing to produce what could be seen as a kind of multinomial cross-correlation. So this is the line of synchronization, where if two systems are synchronized, we should expect the largest density of points. We look at a diagonal shifted slightly above it. We calculate the percentage of points falling on that line. We do that for every subsequent diagonal, and we shifting downward to the corresponding one below it. And the idea would be that, well, this percentage along this line is going to produce a specific value. We do that for every diagonal. And if two systems are synchronized, we should see this maximum at diagonal 0. And in fact, in this plot, this is the kind of thing that you see. So this is akin to a cross-correlation function, or a multinomial cross-correlation function, except that it has some subtly different properties that I'm happy to talk about if you ask it. This is referred to as a diagonal recurrence profile, or a diagonal-wise recurrence. And this is a coupling function between these two systems at the categorical level. So we're taking linguistic level descriptions, topics of conversation, potentially gestures, or specific things people are looking at, and we're quantifying the coupling between those two systems. If the coupling is slightly different, such as an increased strength, we would see a corresponding change in that profile. Okay. So that's essentially recurrence analysis. And so let's jump. I'm going to use this function throughout this talk. So it's a very simple use of recurrence methods, and I'm going to use it throughout the talk. So that sort of cross-correlation function, that many of you are probably familiar with anyway, is going to come up everywhere. So let's look at coupled attention between two human systems who are talking. And the context we're going to look at is essentially a kind of, at least a structural analog to that little neural network simulation I just showed you. And it looks something like this. Imagine hanging out with a friend at an art gallery. You're not looking at each other while you're talking, but rather you're talking to each other and looking upon some shared visual space. So the question is, what do the dynamics of eye movements in that context index in interesting ways some of the fundamental characteristics of the interaction taking place between the two of you? So if you track the eye movements of these two individuals while they're talking about this painting, will those eye movements index maybe some interesting things about their interaction? So let's start with really simple stuff. So with Daniel Richardson, most of this work is with Daniel Richardson, a wonderful collaborator for many years. An experiment back in 2005 where we looked at the temporal structuring of visual attention between somebody who's doing all the talking and somebody who's listening. And so this is just the basic setup. Two people sat in separate rooms in front of a remote eye tracker. And this is an old study, as I noted, so anybody recognize this exciting thing here? This Friends. They all reported familiarity with this TV show, and they sat in front of these different computers and had one person gave a short narrative about some aspect of the show that they found interesting. And one listener was in another room. Their eyes tracked similarly at exactly the same rate. We synchronized all of their data, and we allowed them to listen and track. And in fact, the listeners were told that they would get a comprehension test at the end of this little episode. So we composed a series of questions that could only be answered correctly if you listened to the speaker. So here's a great video that Daniel supplied. The speaker is, you're going to hear the speaker, and you'll see these crosshairs, and you'll see an accurate listener in a light box and an inaccurate listener in a dark box. And I think for me, if you just follow the listener, if you follow the speaker, you kind of get a sense of the pattern of data that will show in the recurrence analysis. Or something like that.
Probably one of my favorite episodes is when Ross and Rachel have a baby together. They're not actually together at the time, but he's in the hospital with her the whole time. And then Joey comes in and proposes to Rachel. He has the ring, and he's on the floor proposing to her. And then Ross walks in, and there's so much drama because it's actually.
So who knows what the inaccurate listener is doing? But the accurate listener is, in some sense, exhibiting a kind of lag function. Following visual attention seems to be keeping up with, but slightly lagged behind the speaker. So what we do in this case is we can coarse grain the visual attention and just grab essentially a nominal time series in precisely the way that we did with the neural networks. We just grab the specific panel that's being fixated by these participants, speaker and listener, over time. This was just 60 seconds of naturalistic data, of eye movement data. 60 seconds of naturalistic eye movement data in 49 pairs. It's a little bit more detailed than methods, but there are 49 pairs in only 60 seconds. So here's an example recurrence plot. It looks, of course, much like the simulation I showed you. These are these little momentary topical attractors while maybe the speaker is mentioning one of the characters and the listener's keeping up, and they're both looking at this character at the same time. And that's what these blocks reflect, is this sort of momentary attentional attractor between these two systems. But you can probably observe along this main diagonal in a certain width around it, you can see that there does seem to be a shift in this function. And in fact, when we look at a super imposition of all of these recurrence plots among all of the subjects, the grayscale reflects where points tend to fall. You can see that there's a subtle shift. And that shift is in a very specific interpretable direction. So the idea is, if you just look at this blue dot, anything falling on this side of the line of synchronization is going to reflect the speaker leading, because it's earlier in time for the speaker and later in time for the listener. And so when we construct that diagonal recurrence profile, that lag function, you now are able to quantify sort of this characteristic timescale of attentional entrainment when one person's doing all the talking. So attentional entrainment in narrative is at its maximum at approximately 2,000 milliseconds. So here are the actual data. It's published in Cognitive Science in 2005. Now I mentioned we had those comprehension questions. So in the dark blue, we're going to have high accuracy listeners, and in light blue, the low accuracy. You can see a clear distinction, the attentional coupling between these two people. So this is in 60 seconds of data. We're capable of identifying in pretty clear ways who's listening and who's not. And so this first demonstration is that using this sort of relatively flexible dynamic technique, we're able to extract this characteristic dynamic structure of the coupling between speaker and listener. And so what do you expect would happen in the context of conversation? So we do precisely the same thing. They're talking about this 2x3 grid of characters. We extract their eye movements in precisely the same way. And here's the diagonal recurrence profile in the bidirectional conversational case. The profile shifts towards 0. So on average, in real-time interaction, while you're talking about a work of art or trying to discern navigation on a map, two people exhibit tightly coupled attentional streams in time. And finally, in this eye movement sphere, in a study that was meant to look at so in these cases, all the participants have this predetermined lingo that they can use with each other while they're talking about these characters. They know the names of the characters and so on. But we wanted to look at how this emergence of linguistic forms would shape the coupling of the perceptual motor system. And so we utilized what's called a tangram task, using almost precisely the same design, but just a subtle change based on a very prominent task that's used in psycholinguistics. So the tangram task, the two people who are talking in different rooms now are given different roles. One is a director, and the other a matcher. And they're given a 2x3 grid, just as they did before, but this time it's being occupied by these crazy tangram figures. And you'll notice that they have the same figures on their screen, but the director is given one of these to describe to the matcher so that he or she can pick it out in the lineup. Right. So extensive work has shown that what happens in this case is that participants who are playing this game with each other come to an agreed, stable, and very efficient form of description for this game. So here's an example of how this might work. So when they first do this task, the director might say, oh, the shape I have to tell you about now is the guy kind of carrying a triangle and walking. And the matcher might say, okay, I got it. Does that work for you guys? Triangle and walking? Yeah. All right. On the second round, the director might essentially shorten the utterance and say just something like, the guy with the triangle again. Yep, got it. And by the third round, they come to this agreed referring expression, such as triangle guy, got it. And so they become a highly efficient coupled system for picking out these kinds of shapes. And so we just asked, do the perceptual motor dynamics in terms of visual attentional coupling index this emergence? And so what we did is what you might do with peak lag analysis with a cross-correlation kind of function. We take this multinomial cross-correlation function, this diagonal recurrence profile, and you can extract all kinds of measures here. Treat this as sort of a distribution. We can look at what the maximum density is. We can look at where that density is taking place. And so this would reflect within a given range of time how recurrent they were at any given moment, across all comparisons, and where did that take place, so who's leading, who's following. And of course you can grab other kinds of characteristics of this function as well. The average level of this function, how kurtotic the function is, the dispersion characteristics, and so on. And so what we're doing in this design is looking at these 20 dyads and just going from round to round and looking at how these visual profiles are changing and the way these two systems are coupled, these two human beings are coupled. So I'm just going to quickly tell you about three measures we extracted in this study. We looked at the maximum recurrence. We looked at the mean level of recurrence, so it was actually a -3 +3 range, which we found in previous studies to be sort of the hallmark temporal region for attentional coupling. And then we looked at the location at which that maximum occurs. And so the idea is that, well, as they're becoming more coupled in their language, we should expect there to be an increase in coupling in some way or another in their visual coupling. But then also this maximum lag, where this maximum is taking place, we would expect maybe move closer to 0, which would reflect this synchronous coupling in time. And so I'll just show you just the results of those measures. In general, mean recurrence is going down while maximum recurrence is going up. So this is characteristic of this temporal coupling that's looking more kurtotic. And so when we're trying to resolve the ambiguity of a description and figure out which shape is being identified, we actually focus for quite a long period of time, maybe on a small subset of those shapes. But what happens over time is that referring system, that highly efficient linguistic system, allows us not to be as recurrent for a long period of time, but highly recurrent for a quick moment. So this would reflect a high kurtosis. And then interestingly, of course, is that we get this shift towards 0. So in the direction of the director leading, we actually get these profiles tend to shift towards 0. So language is essentially organizing these two human systems in this one sort of visual or perceptual motor unit. So what we've seen is that this low-level index, visual attentional coupling, can index just simple narrative, conversation, and also the emergence of linguistic material that's organizing their behavior. So the low-level stuff is indexing the high-level stuff. But so far we focused just on one channel. We've just looked at the eyes. And I've actually carefully set this up so that if I am at risk for loss of time, I can always come back to the music stuff that I added here. Okay. So we've just focused on this idea that changes in the interactive landscape have corresponding changes in this and the dynamics of visual coupling. But as I mentioned at the start of this talk, we're interested in the way in which the multimodal, multi-scale structure of language unfolds. So I'm going to tell you about this large-scale corpus project with Max LaUrsa that used what's called the map task, where two participants wander into the lab, and one person is given the task of giving directions to another. So this is what the task looks like. This information giver is provided with a route. The information follower is given a noisier version of it. And so what happens in this task is they have to use language they can see each other. There's this webcam here. And as you can tell, Max LaUrsa, in his lab at Memphis at the time, there were a variety of other cameras on these members of the interaction. And so what happened in this task, in this map task, is that Max didn't just look at the attention that might be shared between these two people, but almost every other channel that's communicatively interesting, literally. So he composed what I joked to him as I called it the Mad Lab Army. He called this lab the Mad Lab. And he had essentially a massive army of undergraduate RAs who coded at 250 millisecond intervals about 50 channels. So every single one of these dyads engages in eight of these trials. And there are something like 25 of these dyads. So this is 192 interactions, some of which spanning many, many minutes. And so he had this army of undergraduates code things like what's happening at the eyebrows, 250 millisecond intervals. What's happening with gesture. What's happening with different high-level dialogue moves, like giving an explanation or asking a question. Are they smiling? So this is a massive corpus-generating sort of an endeavor, and at 250 millisecond intervals, they're capturing these packets